All right, there we go. Clean break. So what's the point of the Laplace transform technique? Why do we need it? My view is simply this, is it's a tool to solve discontinuous problems. And eventually you learn about Green's functions. Nice, very nice. That's much later, and I don't really think I do it justice in this course, but I'll just say there is a little bit more to it than just discontinuous problems. But discontinuous problems is certainly one of the big things. So here it is. The Laplace transform of a function of time is a function of s. It's equal to the integral from 0 to infinity of f of t e to the minus st dt. Now, you could ask, I mean, obviously you should ask, what? Why? And there are reasons, none of which I can exposit worth anything. I have a link in the notes to about a 40-page discussion by, I think it's Matlack or some, I forget his name, but he's an MIT professor who's been teaching differential equations for who knows how long. I mean, and it's a well-oiled machine. He gets every ounce of every minute. I mean, that course is beastly. I admire it greatly. But he actually has some explanation in there of, you know, why you'd write down such a formula. I mean, I will give you an argument implicitly. It's not a very satisfying argument, but it works. Is really my best argument for you at the moment. And I'm sorry, we'll have to make do with that. So this is the definition of the Laplace transform. What we're doing is we're taking in a function of t and we're spitting out a function of s. All right, so example 1. What is the Laplace transform of, I don't know, 1? So we would integrate from 0 to infinity, 1 e to the minus st dt. What's the antiderivative of e to the minus st with respect to t? Very good. Minus 1 over s, e to the st, and we have to evaluate from 0 to infinity. Of course, that is shorthand for a limiting process. Don't tell the mathematicians I didn't write the limit. Sorry. But you guys know what the deal is here. Minus 1 over s, e to the minus s times infinity, plus 1 over s, because e to the 0 is 1, right? Now this e to the minus s times infinity drops out, provided what? As long as s is greater than 0, we have that drops to 0. We have the exponential of a very large negative quantity. It's 0. So there you go. Your first Laplace transform. Unless you've had that engineering class where you do Laplace transforms, and for some reason we don't have this as a prerequisite. Any of you guys? No? AC circuits, yeah. This should be a prerequisite for that, shouldn't it? I mean, I don't know. I guess maybe that's impossible. I don't know. I've always felt very silly in some sense. I mean, what math do you guys take before AC circuits? Calc 2. See, we should be doing Laplace transforms in Calc 2 then. That's actually not too crazy. I mean, it's basically improper integration. And the algebra that we'll be doing is very much calculus 2 algebra. That's true. Okay, next, theorem. If we have the Laplace transform of e to the at times f of t of s, we get, in fact, f of s minus a, where f of s is the Laplace transform of f of t of s. So this is a pretty usual notation. I mean, I could write script DL brackets f of t of s minus a. That would be the same thing. Here's proof. So those exponentials we can put together, right? That's f of t e to the minus s minus a times t dt, right? Did you guys see what I did? We have the exponentials, like e to the at times e to the minus st is e to the at minus st, but we can write, you know, at minus st as minus s minus a, because minus minus is plus, right? And the reason I do that is simply, you look at this and you go, aha, that is the Laplace transform of f of t at s minus a. See, because instead of having s in the argument of the exponential, I have s minus a. Just plain substitution. It's just, that's it. That's, and my, you know, fine. And that, of course, in the other notation is just big F of s minus a. My example 2 is just notation. If we have f of t equals to 1, then f of s is equal to 1 over s in the big F notation, usual notation. All right. But a lot of times we like to use the script L to denote the Laplace transform because it gives us, you know, a little bit more direct. What happens then? What's the example 3? What's the Laplace transform of e to the at then? It should be what? It should be 1 over s, right? Where we're taking s and we're replacing it with s minus a, right? In other words, it's 1 over s minus a. So the Laplace transform of an exponential is just 1 over s minus a. Oh, this, I don't know, sometimes people might write 1 over s or s equals s minus a. I don't know. I mean, I'm saying evaluate it at s minus a. I don't know what's the right notation for you guys here. I mean, I could also write Laplace transform of 1 at s minus a. That would also be true. The point is I take the Laplace transform of 1 and I replace s with s minus a. Guess what? Complex numbers are awesome, and they work here. And if I had a complex valued function of a real variable, I would still define the Laplace transform just like this, which means I can think about a being a complex number, and this is still legitimate. All right, so what does that mean then? If we let, so in other words, I'm saying that the Laplace transform of e to the, let's say, lambda t of s is equal to 1 over s minus lambda, right? Now, let's let lambda equal to alpha plus I beta, as our custom has been when it's complex. And so that's 1 over s minus alpha minus I beta. Now, do you guys know how to get the I out of the denominator? What do we do to move I upstairs, to put it in Cartesian form? I asked Dr. Pettiford what some of the most important thing I could do in this course would be to help engineering students, and basically you said, well, they need to know how to do complex arithmetic really well. That'd be helpful. So here's a good example of that. I'm paraphrasing. I forget exactly what he said. Something like that. I hear what I want to hear. He said, do complex analysis. Teach them manifolds. Okay, fine. He didn't say that. But what if he had? Let's see here. It's like, we're going to get rid of some humanities requirements so you guys can have more math courses. Like, work on that. That's good. So what I've done is I've multiplied by the conjugate of the denominator over the conjugate of the denominator. This is a standard rationalization trick, right? So what's the pattern here? We're going to have s minus alpha plus I beta upstairs. And downstairs, we're going to have s minus alpha squared. And see what happens? I get an I beta and a minus I beta times s minus alpha. The cross terms cancel. The terms which have a manifest I in them cancel. And we are just left with s minus alpha squared plus beta squared, right? But e to the lambda t is also equal to what? Right? And one thing I have not yet said, but I probably should, is it's kind of important. L is linear transformation. So in particular, if I have L of e to the alpha t cosine beta t plus I e to the alpha t sine beta t, guess what I can do? I can break it up. That's the Laplace transform of e to the alpha t cosine beta t. I can pull the I out because it's a constant. There's that linearity partly in play. Plus transform e to the alpha t sine beta t. Right? And that's all equal to, what was it, s minus alpha plus I beta divided by s minus alpha squared plus beta squared. So we've got a complex equation. So that gives us two real equations. The real part and the imaginary part. So the real part, this guy right here, Laplace transform of cosine t, that's going to pick up this s minus alpha over the denominator. And the imaginary part, this guy, is going to pick up the beta term. So from this calculation, indeed from the Laplace transform of the exponential, I can extrapolate, using complex math, the Laplace transform of exponentials times sine or cosine. The Laplace transform of e to the alpha t cosine beta t of s is s minus alpha over s minus alpha squared plus beta squared. And the Laplace transform of e to the alpha t sine beta t of s is beta over s minus alpha squared plus beta squared. fun exercise. Do you guys know about Cauchy and Cinch? Who has never seen hyperbolic cosine and hyperbolic sine before here? So you guys know about Cauchy and Cinch. Hooray. So just to remind you, just in case you're being shy. Let's see, Cauchy of x is 1/2 e to the x plus e to the minus x, right? And Cinch of x is 1/2 e to the x minus e to the minus x, right? Cauchy and Cinch are respectively the even and odd pieces of the exponential function. Something beautiful happens with Cauchy and Cinch here. In fact, you can prove the following. The Laplace transform of e to the alpha t Cauchy beta t and the Laplace transform of e to the alpha t Cinch beta t nearly the same as what we just derived, except what? Yep, exactly. That's how it works out. Maybe I'll make that a homework problem for you guys. It's fun to work through. See, because exponentials times Cauchy or Cinch are just exponentials, right? Like e to the alpha t, Cauchy beta t is actually what? It's actually 1/2 e to the alpha plus beta times time plus e to the alpha minus beta times time, for what it's worth. So you can derive this using our example 3 in linearity of the Laplace transform. It's not that hard. You got to make a common denominator to finish it. But anyway, to me, it's very satisfying that. Okay, so these are some of our favorite functions. Another one I should mention, and I won't work this out at the moment. Maybe next time I'll work it out. But the Laplace transform, let's see here, example 4, I suppose. I guess this was example 4, my fun exercise. This is example 5. The Laplace transform of t to the n times e to the, well, forget about e to the at. What's the Laplace transform of t to the n? It works out to n factorial over s to the n plus 1. So this is how the Laplace transform of like a polynomial goes. So we can take the, and by the way, you notice that we've got sine and cosine, pure sines and cosines. If you put alpha, what happens if you put alpha equals to 0 in our example 3? A lot of times this is what you need. So a lot of the time I find myself using pure sine and cosine Laplace transforms, right? It's not always multiplied by an exponential. Like a lot of times that comes up. So it's important to know alpha equals 0 is an allowed case. That gives us pure sine, cosine. All right. Example 6. If I have the Laplace transform of e to the at times t to the n, that gives me what? N factorial divided by what? Let's see if you guys actually understand my theorem that I wrote over here. This is usually called the shift theorem, because it shifts the s. Yeah. Can you use the shift theorem on example 6? Given example 5?
S minus a to bm plus 1.
Very good. Yeah. All right. So here's some basic Laplace transforms. This is most of what we need, what I've already shown you. I'm not going to get to the discontinuous thing, which is, to me, really the selling point of it until next time. I mean, like, we need to build up our understanding of this a little bit before we get there. But the next thing we should talk about is how to take the Laplace transform of derivatives. Because that is really where it's at. All right, we don't need this anymore. So let's try that out. What happens if we take the Laplace transform? So this is a calculation. From this calculation, we're going to discover a theorem, okay? So let's try to take the Laplace transform of dy dt of s. So let's see here. That's the integral from 0 to infinity, right? Of what? Of dy dt, right? Times e to the minus st dt. And so you could do integration by parts here. I won't quite do that. What I'm going to do is sort of derive integration by parts again. So here's my observation. What happens if we take the derivative with respect to time of y times e to the minus st? What's that give us? It gives us the thing we have here, right? Then what else? Product rule, right? So then minus sy e to the minus st, yeah? So if you look at that, we already have that term, which is this term here. And so we can trade what's green for the total derivative, right, for this total derivative, and then plus s times y e to the minus st dt. What happens when we integrate a total derivative? Well, fundamental theorem of calculus, like the total rate of change theorem, whatever you want to call it. We get back what we're differentiating, right? Evaluated at the bounds. So this just becomes y e to the minus st evaluated from 0 to infinity, right? And then how about this s? We can pull the s out, right? S has no t dependence, so we have integral from 0 to infinity y e to the minus st dt. All right, so what was this? I mean, what does this give us? This is that's like y of infinity, right? Times e to the minus s times infinity minus what? Minus y of 0 times e to the 0, which is 1, right? Plus what's this thing? That's the Laplace transform of y. So that's s times the Laplace transform of y. Fine. Of t of s. There, you happy? Now, the first term, if y is well behaved, right? The first term drops out because, well, that's, you see, what do you need in order for this term to go to 0? You need something like y is what? Y is not growing faster than what? If y grows faster than e to the minus s, we're kind of in trouble, right? So more or less, if you have y is bounded by some exponential, then it's okay. I mean, in short, y has to be exponential order alpha for the Laplace transform to exist. I've kind of buried that under the rug here at the moment. But there is a condition that you need on the function for the Laplace transform to exist. So it has to be what's called exponential order alpha, sine, cosine exponentials, and pretty much everything we're interested in is exponential order alpha. So we don't get in trouble. I'll probably talk about that next class. Long story short, for reasonable y, this first term drops out, gone. And what we found, right, just to summarize, is that the Laplace transform of dy dt is actually equal to, well, it's equal to s times big Y minus y of 0, where big Y is equal to the Laplace transform of little y. So this is the theorem. Now, once you know that, we can move on and try second derivatives. What is a second derivative? How is it related to the first derivative? Not a complicated question, guys. It's just the derivative, right? Yeah, right. Yeah. And it's not a trap. I really just, so if we were to calculate the Laplace transform of y prime prime, right? Well, that is the Laplace transform of y prime prime, right? So by the theorem we just proved, right? This should be y prime of, well, minus y prime of 0, right? Plus s times the Laplace transform of y prime of s. So I'm replacing y with y prime in the theorem, yeah? If you like, I could restate this theorem in terms of f. df dt, Laplace transform of df dt is s minus big F minus f of 0, like this, yeah? And so where big F is the Laplace transform of little f, and with that notation, you could take, f equal to y prime, if that helps you to see the substitution I'm making explicitly. Right. Now what do we do? Use the theorem on this piece like we just did, right? So that's minus y of 0 plus s times the Laplace transform of little y. So in total, we get s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0, aka the Laplace transform of y prime prime is equal to, let's say, s squared times big Y minus s times y of 0 minus y prime of 0. There's also a corresponding theorem for 3 derivatives or 4 derivatives or 5 derivatives or as many as you like, right? What would the similar formula for y prime 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 be? Let me not work it out. Let me just write it down. See if you guys can tell me. I'll do the easy part. S cubed of y, then what? Minus s squared y of 0 minus s y prime of 0 minus y prime prime of 0. And you can iterate and just keep doing this, right? So the neat thing, do you guys see something that's really interesting about this technique is that the Laplace transform of a derivative does what? There's two really interesting features. One thing is, it's converting differentiation in the time domain to multiplication by s in what's called the frequency domain. For reasons of the application to electrical engineering, the s domain is often called the frequency domain, right? So in the world of s's and big y's, we have multiplication. Whereas in the world of time and little y, we have differentiation, right? So that means we're going to be able to take a differential equation and convert it to an algebraic equation. That's really, really nice because we can do algebra, right? The other thing that's really kind of neat is that it's wrapping the initial conditions into the Laplace transform, right? Laplace transform is tied to the initial conditions, which means we're building initial conditions into the solution we're finding with this technique, which is nice. That means after we do this, we already have the initial conditions built in, right? We don't have to fit them later. That's really cool. All right, so I think we have everything we need to actually work an honest to goodness example. Now, of course, there's a larger discussion of like how do you take the inverse Laplace transform? You know, there's more to do, but I think at this point we can actually do an example, so at least you understand a little bit more about what it is that we're after here. So let's try to solve. We'll start out simple here. Y prime prime plus 2y prime plus y equals to 0, given y of 0 equals to, let's say, 1, and y prime of 0 equals to 2. All right? So the technique here is we take the Laplace transform of the differential equation. All right? So what's that look like? Laplace transform is a linear operator. So Laplace transform of y prime prime plus 2 times the Laplace transform of y prime plus the Laplace transform of y is equal to the Laplace transform of 0. Well, the Laplace transform of 0, good news guys, 0. That's pretty easy to see from the definition, right? If you integrate 0 times the exponential from 0 to infinity, you get 0, right? So what's the Laplace transform of y prime prime? Well, we wrote it over here, didn't we? So it's s squared, big Y, what? Minus s times y of 0, which was just 1. So minus s minus 2, right? That, again, I'm using what we just derived over here to get from this to that. Plus 2, let's see here, that should be s times big Y minus y of 0, which was 1, and then plus big Y equals to 0. Again, I'm using the theorem that I boxed in red a few minutes ago to get from this to that. Now, all these different techniques you learned this semester, they all kind of, in one way or another, will funnel themselves back to the same algebra. The notation may be different, but like the algebra is very much the same. So we're going to get s squared minus, or rather plus 2s plus 1, factor out the big Y, right? And that's equal to, what do we got here? We've got s. I've got a minus 2 and another minus 2, so minus 4. You guys see what I did? I just grouped all my big Y's together, and everything without the big Y I brought to the other side. my goal at the moment is to solve for big Y. Okay? Once I do that, if I can just think backwards, then I'll have the solution. See, if the Laplace transform takes me from little y to big Y, then there's also something called the inverse Laplace transform, which goes the other way. We'll get to it in just a second here, but you guys recognize this, though. This is what? This is just the characteristic polynomial, right? With s instead of lambda. So, all right, so we get y, big Y, is equal to s minus 4 divided by s squared plus 2s plus 1. But what is s squared plus 2s plus 1? Right. So this is really s plus 1 minus 5. If you tilt your head and squint, you can see it. It's there, right? Yes? Yeah?
I think it might be s plus 4. Could be wrong.
Oh, thank you. Very good. Yes, if I have a minus 4 on the left-hand side, I move it to the other side, it should certainly be plus 4. Very good. Thank you, sir. Let's see here. So plus 4, which means that shouldn't be minus 5. That should be plus 3, yeah? All right. Why did I do that? Why is this, was this mysterious step of changing a 4 to 1 plus 3? Why did I do that? Right, here's a law of algebra for you. A plus b over c is a over c plus b over c. Of course, it's worth mentioning, for some of you more than others, that this is not the case, right? I shouldn't even write that. I shouldn't even write it down. But I should strike it from the record. But this is very, very different and wrong. But we can split up addition in the numerator, given a common denominator, right? Okay, so we have big Y is equal to s plus 1 over s plus 1 squared plus 3 over s plus 1 squared, right? Now those cancel, right? So what I really have is I've got Y is equal to 1 over s plus 1 plus 3 over s plus 1 squared. Now, here's the notation we use. We say little y is equal to the inverse Laplace transform of big Y, right? Which is going to be the inverse Laplace transform of 1 over s plus 1 plus the inverse Laplace transform of 3 over s plus 1 squared. So what's the inverse Laplace transform of s plus 1? Well, here's the way that works. The Laplace transform of e to the minus t, right, is 1 over s plus 1. So this says that the inverse Laplace transform of 1 over s plus 1 is actually equal to e to the minus t. So what we get is that y is equal to e to the minus t. And how about that? How can we get 3 over s plus 1 squared from a Laplace transform? Let's see here. This would say that the inverse Laplace transform of 1 over s minus a to the n plus 1, right, would be equal to e to the at times t to the n divided by n factorial, right? So if we look at the case inverse Laplace transform of 1 over s minus 1 squared, what do we get? N equals to 1, right? 1 plus 1 is 2. So we get e to the oh man. Sorry. I may have a sign error here. I'm sorry, a is equal to minus 1. I'm just an idiot. Okay, so e to the minus t, right? Duh. I'll get with it eventually here. T divided by 1 factorial, which of course is just, t e to the minus t, right? But we don't just have that. We also have this pesky 3 here, right? So this gives us plus 3 t e to the minus t. What's that? No.
Can you separate out the e to the negative t?
Oh yeah, of course, we could factor that out. Yeah. And you can check that that works, right? If we plug in times 0, we get 1. If you differentiate that, you'll be able to see when you plug in 0, you get 2. So the basic algorithm is this. Step 1, we take Laplace transform of our differential equation, right, to convert to a y and s equation, right? Step number 2, solve for big Y. Step number 3, little y is equal to the inverse of the Laplace transform of the big Y. So we'll find big Y equals to stuff. So little y, the solution we're after, is the inverse Laplace transform of that stuff. Devil's in the details. To make the stuff here was this was what I'm calling stuff, right? That was the stuff. And there, for me, it just took writing 4 as 3 plus 1 to break it into 2 pieces, which I could see how to take the inverse transform of, right? But if you think about other differential equations, you start to realize that what that stuff looks like, how to unwind that to go back to little y, to break it into pieces which are inverse transformable, well, that could be more complicated. In fact, that's why I can't explain the method to you in 10 minutes. It's going to take me a while to explain our usual techniques for calculating inverse transforms. But much like you have to differentiate before you integrate, the first order of business is to just learn the basic Laplace transforms, and then we start trying to think about how to go backwards. So, hey, by the way, though, you notice that this has given us another way to understand where the t comes from in the repeated root case. Although I think that this is kind of a more exotic proof. I mean, I didn't explain to you, I have not derived this yet, have I? But, yeah. I think we've got enough time for that, so let's end today with that. So let's see here. Suppose we have the integral from 0 to infinity of how's it go? Y e to the minus st dt. Right. What happens if I differentiate this with respect to s? Now, here I have to do something a little bit underhanded in terms of analysis, but in fact, the integration and the differentiate, you can do them in either order. So I can pull the derivative inside the integral because the integration's over t, whereas the differentiation's over s. Technically speaking, I'm interchanging two limiting operations, and whenever you do that, you're possibly getting into trouble. But if we have assumed that y is of exponential order alpha, then the convergence is uniform, and so this is allowed. But admittedly, there is some analysis that I'm sweeping under the rug right here. You guys will forgive me for that, yeah? Now, y is a function of time, right? So I can pull this out, right? And so I have integral from 0 to infinity of y. So what's the derivative with respect to s of e to the minus st? Right, yeah. All right, so we can pull a minus out of that, and we get minus the integral from 0 to infinity of t times y e to the minus st dt. Aha! So, therefore, the derivative of the Laplace transform with respect to s is equal to minus the Laplace transform of t times y of s. See, oh, I'm sorry, I should be using big Y, shouldn't I? I'm an idiot. It's here. This is big Y, right? So I'm showing the derivative of the Laplace transform of y is, in fact, the Laplace transform of t times y with a minus. What if we took the second derivative? What would d squared y, ds squared be? In fact, the nth derivative of the Laplace transform with respect to s would be equal to minus 1 to the n, the Laplace transform of t to the n times y. So this is a pretty nice identity, right? Now we can easily derive example 6. So apply this. What should we do? Let y equals to 1, right? Then big Y is what? 1 over s. That was our example 1, right? What happens when you take n derivatives? Well, what's y prime? We'll start out small. Y prime is what? DDS of 1 over s, which is what? One over s squared, right? What's y prime prime? Looks like 1 over, well, it's minus 1 times minus 2 s cubed, right? You can start to see the pattern. The nth derivative of y is going to be minus 1 times minus 2 times minus n over s to the n plus 1. Of course, that can be rewritten as n factorial times minus 1 to the n divided by s to the n plus 1. So that's what my derivative of y to the n-fourth power is here. And that should be equal to minus 1 to the n the Laplace transform of t to the n times 1, right? So the minus 1 to the n's cancel, and we obtain that the Laplace transform of the nth power of t of s is actually equal to n factorial divided by s to the n plus 1. And there you go. That was our example 6. This technique I just used of differentiating under the integral doesn't get enough airtime in your calculus courses. It's a really powerful technique which is vastly underused in our current curriculum. Well, I'll let it end there then. See you guys when? Oh, Monday. That's right. I owe you a quiz.